How many people have heard of gRPC? Great. It's very much an introduction to gRPC. A lot of this tech is explained in very complicated ways, so the goal today is to really talk about it at a very elementary level so people can understand what the tech is and what you should do with it next. It is 1:30 now, so I'm gonna go ahead and get started. These go so much better if I have like an MC to intro me, so I'm gonna intro myself. All right, so your next speaker is Kelsie Hightower. Hold on, let me full screen this thing. Gotta make it legit. All right, your next speaker is Kelsie Hightower. He's coming all the way from Portland, Oregon, by airplane, not bike. I work at Google. I'm a developer advocate on the cloud platform team. He specializes in Kubernetes, Golang, and learning a lot more about gRPC and this application level frameworks. So with that, let's give Kelsie a big warm applause. Yeah, like he said, I'm Kelsie Hightower. I'll be talking about building microservices with gRPC and Kubernetes. This is a very ambitious talk. We're going to be covering mainly 3 things in this talk, and we'll see that in the agenda. The first thing is I hate microservices. I just think they're just applications. I know people have sold a lot of books and consulting based on that word, microservices. But the truth is, gRPC is great just for any application you're building. We're going to talk about some of the things that it's good at, and maybe you'll see some things that it's quite not great at. So in this agenda, we're going to have to cover 3 things to give you a solid understanding of gRPC and some of its goals. Number 1 is protocol buffers. All right? How many people have heard of protocol buffers? Great. So we're going to level set just to make sure everyone's on the same page. And once we understand protocol buffers and what that can do for us, we'll turn our attention to gRPC and using protocol buffers to describe services, right? So instead of rolling your own RPC mechanism or just using protocol buffers to pass messages back and forth between 2 clients and a server, we'll use protocol buffers to generate our server bindings and our client stubs. And then we're going to talk about Kubernetes. And Kubernetes is what we're going to use to deploy our application, right? And most of our applications we'll see will require things like TLS certificates, tokens, things to validate tokens. There's a lot of moving parts when you start having applications, and most frameworks fall down because they don't cover or offer all those things. So we're going to talk about how gRPC, when combined with Kubernetes, I think gives you that complete platform from application all the way down to even the application infrastructure level. So we're going to talk about protocol buffers really quick. So binary serialization interface. This makes sysadmins want to cry, because it's not JSON, right? Most people are used to being able to use curl to interact with every service and visualize via ASCII or something on their terminal what comes back, right? So this is the biggest challenge for most people adopting or moving to gRPC. So even though it will work and give you a lot of benefits such as speed, performance, lightweight on the wire, this is where most people push back, right? They're willing to forgo all of those benefits just for the fact that they can't use curl, right? And as the ecosystem improves, I think we'll see more tools that give us some ways to inspect protocol buffers as it's in flight. The other one is definition language, IDL. So this feels very enterprisey to me, right? It's like you have to kind of define this IDL of what you plan to do, and there's a lot of ceremony in that. But the benefits, I think, can be tremendous, and we'll try to see what that looks like. And then maybe the biggest benefit is cross-language support. So this is where, like me, I'm a Go programmer, and I hate all languages right now, right, except for Go. So for me, I just want to write things in Golang, and then hopefully do as little coding as possible to support my clients, okay? And then this is what some of the things that protocol buffers and gRPC attempt to allow us to do. The first thing that most people trip on is protocol buffers. How many people actually got protocol buffers set up on their laptops? You should totally get a medal. This is where most people trip up when they go to explore gRPC and protocol buffers. The first thing you need to do is have a dev environment. So on my Mac, I use brew install Protobufs. So this gives me the Protobuf compiler. So it takes my IDL and spits it out in various languages based on the plugins that I'm using. The next thing is I need to get a plugin for my particular language of choice, okay? So on the gRPC webpage or Protobufs webpage, we talk about all the languages that we support. The idea here is to give us this binary encoding that's efficient, but the thing is we need to be able to generate it. So we're going to see what that looks like. Your workflow really quick. You define your messages, right, using the Protobuf language. You compile it using the Proto-C command line tool, okay? And that's going to generate output in the language of your choice that we support. And then you need to consume the results, right? And this is where most people get lost because they think there's magic. There's no magic. You still have to do some development work. But we give you a better starting point by generating most of the stubs that you need, right? So you can be using Node.js if you're a hipster. You can use Go if you're cool. And you can insert your enterprise language there. I think Java has decent support, and C# does as well. So let's walk through this really quick. It took me a while to really grasp this workflow because no one explains it this way, right? It's like this high performance thing that only the big big web scale shops do. So to look at this really quick, we're going to look at a simple IDL for a user, okay? So this is the case where you're thinking about taking protocol buffers and replacing your usage of JSON, right? Some people have done some benchmarking and profiling. If you're using YAML, your servers are probably overheating. If you're using JSON, you're probably doing a little bit better because it's not as a complex spec and a little lighter on the CPU. And some people get to the point where they spend a lot of the time in production encoding and decoding JSON, right? This is crazy, especially for high-scale web services. I think SoundCloud did a report recently, almost 70% of the CPU time, JSON back and forth, right? You're not serving users if you're just deserializing JSON all day. So what do? We try to move to protocol buffers. So what we do here is we're going to write our proto file. Here I'm using protocol buffers 3, which is kind of a requirement for using gRPC, and we'll get to that later. And here I'm just defining, in Golang this would be a strut. Other languages, you have different ways of defining this, but here's basically a type. This is a user type, and it has a couple of fields, an IDs, an integer, int32, a bunch of strings for name, city, state, that sort of thing. This should look very familiar to most people that are using any programming language, right? So you define this in this intermediate, and then we're going to compile this to our language of our choice, okay? So we define this, and our goal is to get something that I can just import into another language and interact with the results. Why did we do this at Google? If you're just using like raw JSON or raw XML, you're relying on the developer to know all the fields they need to care about. Sometimes you miss one. You ever miss one in production? It's real bad, right? You find out that, hey, you know, it turns out that we owe everyone like 50 extra bucks. And the goal here is to make sure that the developer has to do little as possible in order to use this. So now we have this IDL specified, we need to compile it. So this is a command that I can never remember. Now here's the first gotcha. You need this Proto-C to actually compile this, and you also need to plug and install. And we saw the steps to do that earlier. So I'm going to get Proto-C here. I'm going to compile my code. As a result, let me delete this so you can see that it's pretty fast. Let's try that again. All right, so now we get this generated code. Now, if you're one of these people that follows the style guide of your language,
actually, it's worse than that because that only works because you're in the same directory.
Well, it works if you go up as long as you get the paths correct.
Yeah, you need the -i flag if you're in another directory.
I'm trying to make it easy for folks. So a lot of our docs show you all these crazy paths. You get lost. I'm trying to make it simple for you. Keep it simple. Now, if you pay attention to your style guide, this will make you cringe. Do not look at the generated code. Do not fix the generated code. It's generated code, okay? They tried their best to do things somewhat the right way. There's a lot of purists in a lot of language communities, especially in the Go community. If they've ever saw you do this and try to check in something, I don't think GitHub would accept something like this by default. So the generated code here is basically everything we need to serialize and deserialize one of those user struts, right? And we try to do a lot of things to make it as fast as possible. So we trade off some ugliness in the code for some speed at runtime. Okay? Now, can anyone tell me what this block does? You ever seen this block? What is that? Does anyone know what that is?
254 bytes of the gzip file descriptor parameter.
Oh my goodness.
Yeah.
I don't know what the hell that is. I think this is someone hiding even more code that's pretty bad and decided to just zip it all up so you can't see it and then unzip it at runtime. So now we have this kind of state machine that's perfectly tuned for that one particular piece of code, okay? So now what we can do is we can start to use it, all right? So how would you use it? The first thing I'm gonna do is kind of look at some testing code, all right? So this is a quick way to see it. So here we're in Golang. I have the strut. This is a user strut. I'm using the native semantics of my language. So right here, I don't even know I'm dealing with Protobufs right now. So right now, I generate the code. I'm using the user strut that was generated for me. And here, I'm basically going through, and I'm going to do some benchmarking on Marshaling, Protobufs versus JSON, all right? We're gonna try to have a little competition here. The winner should be obvious, but how bad it is not quite clear from here. So we're gonna marshal our user strut using Protobuf, then marshal it using JSON, and then we're going to unmarshal it using both again, all right? Now, which one is going to win? This would be embarrassing if it goes the other way because of some weird bug, but we're gonna try it anyway. So I'm gonna use my Go test tool. I'm gonna run a benchmark here. So here we're going through and we're doing as many iterations as we can with Protobufs. So on the first step of marshaling the user, we're a little bit faster, maybe about 50%, right? But look at what happens on a deserializing, right? So your clients are sending you JSON on the wire, and you're spending a ton of CPU just to unpack it. This is a waste of time. And this has pushed many of the larger web shops to do something else, right? And this is where binary protocols come in and do really handy, especially when we have code that's tuned for doing that. Most developers probably wouldn't write or sit down and write their own JSON parser to get the same speedups. This is why we just generate the code instead. The next thing we want to do is look at how much it saves on the wire. These are the two main things for Protobufs: being fast and being lightweight on the wire or in your data store, okay? So what I'm gonna do now is I'm going to create two files using the same user strut. All right, so we come down here. I'm just gonna put 1,000,000 entries here, okay? So I'm just going to go run, main.go. All right, so which one of these is going to be bigger?
JSON.
What if I told you were wrong? It's like, dude, you just negated your whole talk. All right, let's run this. Okay, so the JSON one is almost 100 megs bigger. Now, one time I gave a section of this talk, and guys like, well, if you compress it, there won't be much of a difference. And he got me for a moment, because I didn't have time to compress it. But what do you guys think will happen if we do compress this? How much of a difference will it really make? Throw out a number. 50%? 50%. Yeah, this is kind of bad to do during a live demo. Doing these currently on my MacBook Air. If the fans come on, that's what happened. Let's see what it does. You guys are saying 50%. 80%. 80%. Very confident you are. You're pretty confident. Will it even finish, though, on my laptop? Silly me. It's like he's an idiot. All right, let's go. Come on. So you just want to look at CPU usage. You're like, oh, we're probably already finished now. All right, let's see what we got. Okay, we're done. So 50%, 80% is still 3 times smaller, even when compressed, right? So it's a big deal that no matter what you're doing and tuning on the other side, there's still a big benefit for using protocol buffers. That's it for protocol buffers. That's the whole game. There's no other magic. Using it when you have no users, that is premature optimization. You have no users. Focus on getting the customer first. But when you do get a lot of them and you're having problems, this is the key. And this is really important on the mobile space, right? You're chewing away on someone's data plan, they will hate you. They will delete your app, right? So save some bandwidth and resources. That's it on Protobufs. Simple. You're trading JSON for protocol buffers because you want speed and you want size. That's all there is to it. You got to make a decision on when you want to do that. Some people can do this with their existing protocols. You're still using HTTP. You trade out that JSON body for a protocol buffers body. But then you have to pay the hit on being able to debug it because now you're dealing with a binary protocol that is not self-describing. right? So if you don't have that proto file, you can't make sense of it. Next thing is gRPC. All right, so gRPC supports actually protocol buffers and JSON underneath. And then it uses HTTP2 because it's new and shiny, and it supports streaming, right? How many people have got streaming working with their applications? What are you using? Socket.js. How's that working? Okay. See? I'm gonna make it better. I think we can make it better. HTTP2 is really nice because we're starting to see default implementations everywhere. And the idea here is that we get a protocol that works with existing firewalls and should be the standard across all clients and even browsers as soon as people can update their browsers. And it's also a general framework for doing things like logging, security, and tracing. Now, this is the big thing that I think we do not communicate well about gRPC. It's more than just RPC between two endpoints. The goal is to give you a complete application framework. Security, monitoring, everything you can do by intercepting the calls between the server and the client, you should be able to do with gRPC. And we'll see this as we start to get to some of the deployment scenarios. So RPC is just one fragment of it, but if you think about what gRPC and its roots, it comes from an internal system at Google called Stubby. The same team that works on Stubby that provides the complete application framework for all developers is also leading the charge on gRPC. The goal is to hopefully roll out gRPC and replace Stubby. It's gonna take a while, but the nice thing about gRPC is being done with the community in mind, right? So we're not gonna just use all of Google's tools, we'll integrate with things like Prometheus, service discovery tools like Console and etcd, and then again, mobile. Let's talk about gRPC's workflow. You define your messages. This time you're gonna define services right next to the messages you want the clients to pass between each other, okay? You go through the same process where you compile these things, but now instead of just consuming, you're gonna have to implement, right? And I think this is the thing that throws people off. We do not generate all the code for your application. We have no idea what the business logic is for your application, but we do give you the stubs and interfaces to make sure that your clients and servers know that they have to pass specific messages between each other and can expect specific responses between each other, right? So I've seen people give up on gRPC because they thought it was going to do more. If you find a tool that generates your business logic, you probably should look for another job because once your boss finds out, you're done. All right, so you have to implement the server component. You also have to implement the client component, right? But it gives you a much better starting point, and we'll see what that looks like really quick. So once you have your stubs in place, you can write your server in whatever language you choose. You can write your clients in whatever language you choose that we support in gRPC. All right, so I'm going to go through this part really quick to show you what it's like to write a hello world gRPC application. And then we're going to zoom through some of the features of gRPC. Then we're going to talk about packaging it up and run it on something like Kubernetes. All right, so very similar workflow here, okay? And remember, there is no magic in this. So what do we need to create a server that uses gRPC and protocol buffers? What do we need first? Protos. We need our protocol buffers. You got it. So here, we're just going to define this at the root of my project. So it's kind of busy what's going on here, but I have a couple of binaries inside of this source tree. And in the source tree, I have a package called Hello World. I'm going to make a Hello World application using protocol buffers as a starting point. So I'm going to take Hello World, and we're going to look at the proto really quick. Let me just put this on the screen. So very similar. This package is called Hello World because I'm going to import in my Go application. Here we're defining a service. So at the bottom, we're doing what we were doing before. We have two messages. So instead of it being just a user, here I'm just saying I have a request message that inside of it there's a name. And we can grow this over time. Notice that they're numbered. So if I have new versions of my application, I want to stay backwards compatible with old clients, I increment that number. Old clients ignore new fields that it doesn't understand, but they don't break. The goal here is not to delete fields. If you delete fields and protocol buffers, developers will hate you, right? These things are important, and do not well, you can delete the fields, but don't reuse the numbers. And then here's a response. You give me a name. Where do we go? Do we start running something? Okay, you give me a name, I give you a message back. Pretty straightforward. We have one function called say hello, takes a request, returns a response. This is it. And all we need to do now is generate our stubs. So this is where things get a little different. Again, to make the world easy, we're going to cd into that path. I can't remember this, so normally I keep it somewhere near the actual source code. All right, we generate our code. So now we look at our output. Remember, do not look at generated code. So at this point, we now have the Hello World client and server stubs. Now let's implement our server and our client really quick. Now, once you generate your protocol buffers, that's it. The developer that's responsible for managing that is the one that normally does this, so your end user downloading your project should not be recompiling the protocol buffers. Just want to throw that out there for people new. You check in the results with your repository, and you leave the protobuf files nearby. In a lot of cases, if you have multiple languages that you're dealing with, you may choose to centralize your protocol buffers in a central place that all the languages can actually generate their bindings from, right? That's a gotcha that most people fall down on. All right, so now what we're going to do is look at our server implementation. Remember, we're going to keep this really simple. Here, I have some logging set up. I'm using the net library in Golang so I can get a listening socket. And then here you'll see a pattern that we often see. People will do their import and give it an alias, in this case PB. Let me know that this is something that was generated for me. I'm using protocol buffers here. In Golang, we have this context package. You'll kind of see how it works in a moment. And then we also bring in the gRPC library. And every language will have its own implementation of gRPC. So in gRPC, we'll provide a lot of tooling for us, but we also need to bring in our stubs. Here, I'm bringing in the stubs so I can implement the server. Now, in my generated code, there's an interface. And in that interface says, you need to implement a function that says, hello, takes a context, takes a request from the client, and then returns a response and an error. Okay? What is the context for? You ever have a client in HTTP and you want to send the server some metadata, authorization header, something that's not necessarily a payload, right? So you have to have all these specialized headers. So in protocol or in gRPC, we can use that context object. So you can think of it almost as a key value store that gives us metadata and can also be used for things like cancellation. So I'm the client, I kick off this long running thing, I can close that or I can call done on that context and it will propagate down the stack, telling the server and any other code that it called because that context will be passed through the rest of the stack, right? This is important and it's a key for actually making these things that shut down cleanly. Really easy. I'm going to return the PB, remember that's the alias for my hello world package, a response, hello username, right? So this is my implementation. Down here is just boilerplate. I'm just saying I'm starting up, got a listening socket, and here's where we use the gRPC package. You're going to have one for your own language. I'm going to create a new gRPC server, and this is going to deal with the other part of the boilerplate that I don't have to deal with, right? This is just to make things easy for you. Here, I'm going to register my greeter service. So I have this strut that I define the method on. That's my implementation of the greeter server that was generated. Here, I'm saying that I started successfully. I'm going to serve, right? That's about it. You notice I'm not dealing with JSON at all or serializing anything, right? The client's going to pass me a message. The framework's going to take care of that for me, all right? So then we need to build the application, not LD. I do have these built already because I don't want to waste time building them. So I have this server. Okay, so this server just runs on port 10,000. It's up and running. Now let's look at the client implementation really quick. All right, so here's the client implementation. This is pretty straightforward. We got to bring in our protocol buffers again. Server and client stubs are in that same package. Okay, here I'm basically have some flags that tell me where the server is, the name argument that I'm going to pass in. Here I'm going to connect to the server in insecure mode. Okay. Now, this doesn't work with HTTP2 and Golang, and some languages may balk at you if you're not using actual certs, but we can actually do this here because I'm not using some of the HTTP2 features, which is okay now for this part. So here I'm connected to my server with insecure. I'm going to basically close this connection once I'm done with it. And then here from my client stubs, I have the client code that just takes my connection to give me the client greeter that I need to talk to that service. And if you've ever used any RPC before, here I'm just calling that function, giving that context, just in case I want to cancel later or give additional metadata that we'll look at. And then I'm just giving it a request. Again, I don't have to deal with serializing or marshaling anything here. I'm just giving it the PB request, which is already generated for me, giving it its values, and then I'm going to print out the response from the server. This is pretty straightforward here.
Is that going to execute it in its own go routine?
Which one?
The client.
Oh, the client is a whole different binary.
No. Is the say hello call in the client going to execute in its own go routine?
It depends, right? Yes. So if I'm just making a unary call, I'm just going to block. And we just stay in the current go routine. That's implementation detail. If I'm streaming, I will probably get back a streaming object that I can iterate over. So if I'm in Golang, it's probably going to be some channels and things happening behind the scenes. If it's in Java, it's all implementation specific about what will happen there. But in Go, you're probably going to get a, we'll see when we get a streaming server, we're going to get back an object that has channels hooked up to it. But it'll be invisible to you. So I'm going to give it a name. That's it. This is very straightforward. gRPC is nothing more than that. Protocol buffers, speed and efficiency. gRPC for supporting multiple clients in various languages and giving you a head start on generating the stubs for your server and the stubs for your clients. Now, some other things that we get as well. We also get a framework for doing authentication and things like streaming. So I'm going to show you a streaming client really quick. Now, in order to do streaming, we need to do something slightly different. All right, we're going to speed through this piece really quick. All right, so hello world. And now we're going to update a new method that supports streaming. So we'll say set hello stream. And then we'll just say we're going to give a streaming response back. All right? So our goal is to implement that. If you think about the implementation for this, it would be you get a request. Maybe it's a stock ticker. They want to know what the stocks are for a particular ticker. And all you have to do is just stream back the ticks as they come, as the price changes, right? And the client will sit there and just receive them on its own terms or disconnect when it's ready, right? So we're going to do this. What do we have to do once we change that? Change your protos, you got to do what? Recompile. I watch people for hours update that file and do nothing else. We're not going to look at the code that it gets generated. You can on your own time. I'll put all this stuff on GitHub, but I don't want to bore you too much here with looking at all this code output. Now, what we do have now is our streaming server. I'm just going to show you the implementation of the streaming server really quick. So for the streaming piece, we're going to focus here, okay? On that block, we have the stub generated for us. All we have to do is the implementation. We're going to get in a request, and we're also going to get the streaming server, right? We're not getting a context this time. The context is going to be on that actual streaming server that gets passed in. And all we need to do now is your implementation. In this case, I'm just doing a simple for loop and just sending the username or the greeting over and over again. Put your business logic there to stream to the client. If your language supported, you can put that in a Go routine and stream, in a background. But this is up to you. But it makes it really easy to do this kind of streaming thing. Now it goes bidirectional, but I'm not going to go into the details there. But it's pretty much the same thing. The clients and servers can send things back and forth to each other. So here we just run this. So after we do the implementation, we compile it. All right. So we have, there's no flags on this guy. So it's up and running. Now look at the client really quick. Again, super simple stuff here. All right, streaming client. All right, let's look at the implementation. So we do our boilerplate. We connect again in secure. And then here, I'm basically saying, this time I'm going to call the stub that was generated for me. I got my client, have my stub. I give it a context. I give it a request like I did before. But this time, I'm going to get back a stream. When I get that stream back, it's up to me to process the stream. Here, there's a Go channel, or there's a Golang channel behind the scenes here, and I can loop through and call receive on that, and basically get the next message from the client, right? So we have this way of communicating back and forth. But it's just this simple, right? There's not a lot of boilerplate going on here. You grab a stream instead. So we'll run this really quick. We need to give it a name. All right. And we see that it's just streaming back. So when I control C here, that sent the cancel to the context earlier, and now we're back up and running. So now we just get the stream, and you can put any business logic you want here, okay? All right, so that's that piece. So that's gRPC. We're going to show one last thing, which is the security piece, and then we're going to move on to deploying this with Kubernetes. Now, security is where everyone punts in all their gRPC demos because you need things like certs. And then how do you manage distributing certificates? This is the biggest pain, I think, when it comes to actually doing security properly. So we're going to look at really quick what we need to do on the cert side. So if we look at our secure server, I'm going to do a couple of other things. We're going to use tokens as well. By default, gRPC does not ship with anything that understands your tokens. You're going to have to implement, we have a credentials interface. For JWT, it's pretty simple. How many people have used JWT tokens before? I'm going to show you what they are really quick, and then we'll move on quick. So a JWT token looks like this. All righty. We'll grab this token. And then we'll go to one of these services that just wants to steal my certificates, I know. We'll drop this token in here. And inside that token, as you can see here, there's a bit of metadata as well, right? These will be called claims, right? So the idea with the token would be you authenticate username and password to some auth service. The auth service generates a token, maybe stuff some things about the user, what groups you're in, email address, something that other applications in the stack can trust. Gives you that token back, and you can pass this token around. Why do we do this? Usually for performance and keeping the other applications away from the authentication database. All right? And if we put our public key in there, we can verify it, right? So if I wanted to verify this signature, I need to use the public part of the certificate that created or signed my token. All right, so here's my certificate. Do not put your private key in sites like this, pretty crazy. All right, so we put it in there and then the signature is validated, right? And this is what we're gonna have to do on our gRPC servers if we want to have it secured by tokens. All right, let's race through this really quick so we can get on to deploying these things. All right, so now we want to do a secure server. All right, so in the secure server, there's a lot of code here, and I'm going to breeze through it really quick for you. The first thing we're going to do, sorry for this resolution. The first thing we need to do is get some certs. So here, there's a bunch of flags. Oh man, this is a mess. Here, I need to get certs to actually listen on a secure endpoint, so I'm going to grab my key pair. And then also, what I'm going to do is load up a JWT public key and stuff it inside of my server so I can use it in between calls. Now, in gRPC, we support two types of passing of credentials and authentication. One on the connection itself. This is usually done with TLS client certificates. And one per RPC request. So for each function, you can have it require a different set of credentials if you wanted to, right? So I'm just going to show you the implementation of this really quick. So on the secure server, one of the implementations looks like this. Here. Let's look at main again. So here all I'm doing is on those same interfaces we had before. Let's start with this say hello. All I'm doing here is the same implementation details, except for I'm grabbing the token from the context, taking that token and validating it, and then going through my same flow. If I wanted to, I can grab claims out of that token. But this is very much the same thing, except for if you want to require tokens, you need to grab it from the context. This is something that's not quite clear when you get started with gRPC. All of those things get stuffed in your metadata fields. What does a client look like? And the secure client, now what it does is it will grab its token and stuff it into a credentials provider, and then also grab a CA PIM so I can trust the actual cert, especially if I'm using self-signed certs. Here, all I'm doing is setting up some boilerplate so I can actually trust the endpoint that I'm connecting to. Here, I'm using this new implementation of JWT. So I'm taking this token file and creating what we call creds. And you'll see this in the documentation regardless of language. You'll have to deal with a set of credentials. So here, I'm doing one on the transport layer, which is TLS for the server cert. And then here, I'm doing one per RPC, which is my JWT token. So the server on the other side can grab my token out and validate it. And then I connect, all right? So now what we're going to see is that when you deploy one of these things, here's the problem most people have. Look at all this stuff that you need. You need this certificate to be in the right place. You need the server-side certificate to be in the right place. All these things need to coordinate. On the client side, you need two other things to be in place. You need your token, and you need your certificate as well to trust the other side. So how do we deploy these things? All right, so that's gRPC in a nutshell, and now we're going to talk about deploying these things, right? So you're buying in on this efficiency thing. You're buying in on, oh, the last thing I didn't show you was Node.js people. There's one Node.js user in the crowd. Where was he? He didn't raise his hand now? Okay. All right, so here.
If you were a Node.js user.
Ouch. Node.js is the bomb, by the way. All right, so here's the nice thing about protocol buffers. So we saw how it worked for Golang, but look at what we need to do for Node.js. This is kind of nice because what Node.js does is it dynamically pulls in our protobuf. We just give it its directory. It compiles it on the fly. And then it makes our stubs available to us. So we don't have to pre-compile them, right? You just share the actual protobuf file. So if I should, I could be able to, or if I can, I should be able to run this. It'll compile this whole thing on the fly, grab my protos, compile it, make the stubs available, and I should be able to call my service. So I have the server running here. And now we'll do, what is this, like Node? Can I just say Chrome browser? That doesn't work. Client and client.js. And it connects to the server. So for Node.js, it's actually pretty straightforward to adopt protocol buffers. I hope some of the other dynamic languages are or as simple, because compiling these things can be a pain. So with Node, all you have to do is bring in the libraries, and you don't have to pre-compile. All right, so it's on to deployment. All right, so now we have all these artifacts. Now we need to deploy it. This is where Kubernetes comes in. What is Kubernetes? It's a framework for building distributed systems. Loaded term here. For most people, if you got everything on a single machine and you have a lot of system administrators, you're going to be fine, okay? If that is not you, or you don't want that to be you, you might want to look at a tool that can manage your application across multiple hosts. Now, this is where things get tricky for people. Kubernetes is also a scheduler built in. How many people are using a scheduler right now? Woo! This is like magic. When you see this part, it's going to be like magic, I promise you. I'm just going to show you. All right, so Kubernetes, we take your binaries that we were building this whole time, and we're going to stuff them in containers. This is a requirement. All right? Kubernetes doesn't schedule single containers by themselves. We create what we call a pod. So a pod is a logical It's a logical abstraction around one or more of those containers, right? If you're writing something, let's say in Node.js, sometimes you'll read in the documentation, put Nginx in front, so it can be a web proxy. Those two things are tightly coupled, so they should live in the same pod. The pod is also where we put volumes. So if we need secrets for a particular server, the pod is where we define what secrets we need mounted at runtime. This solves the key distribution problem for many people. You don't have to manually copy certs around to all the servers. Kubernetes will do it for you. The next thing is, even when we have multiple apps, they share one IP address, so each of our applications could bind to whatever port they want, even on the same machine, because we give them their own network namespace. If you think about this at a very high level, the pod almost feels like a virtual machine, even though there's no hypervisor on the particular server. All right? So full isolation here using containers, and this wrapper we call a pod, so co-located things are deployed together. That's how you think of a pod, all right? That's the lowest level thing we schedule in Kubernetes. We talked about that scheduler thing, right? Today, you may have sysadmins that place all of your workloads carefully on various servers based on whatever's in the spreadsheet. You got a spreadsheet? He's smiling like, ooh, he started the spreadsheet. You. So we want to get out of the spreadsheet game. In order to get out of the spreadsheet game, we have to declare the state of the infrastructure. This is what Kubernetes is about. So we have those microservices that we created or applications we created. We need to describe how many we want. So let's take that secure server. We're going to say we want one of them running somewhere in our infrastructure. The scheduler's job is to figure out which one. Now, the way it works is based on a set of predicates. Who has the most CPU? Who has the most memory, right? There's various things that you want to weight these things based on. In this case, we would say, you know what? I just need one of them. I'll pick node 1. because they're pretty much even. I can just randomly select one. Now, I want to change the state inside of the cluster manager to say, you know what? I really want 3 of those things deployed. So we make our state change, and then Kubernetes goes out, looks around, the scheduler starts to score these things again and figure out the best place for the next 2 so we can get to the state we want of 3. So now we have 3 total. Why is this important? What happens when servers go down in your infrastructure today? On call. How many people are on call? It's called sleep deprivation, right? The pager goes off, you're like, damn it, where's the spreadsheet? You figure out what needs to be moved. This is real life, right? So in Kubernetes, since we have this declaration inside of the cluster manager, even when the node dies, we know that you wanted another one, so we move it, right? So we just move the application and restart it somewhere else. And ideally, that should hold the pager off, because hopefully you're not tripping alerts on blips, okay? So now we can keep our state, or we can keep our cluster in the desired state. But what about those certificates, right? It's easy to deploy things and build these big images that have configs baked in. Don't do that. In the Kubernetes world, what we can do is create those certs and give them to the cluster manager, and the cluster manager will store all of our certs and secrets in our secret store, and then allow you to reference them later. So in this case, I'm going to point to my directory with all of my secrets in it, and I'm going to do a deployment. The deployment will reference those secrets, and then the secrets will actually score or the cluster will score one of those nodes, taking my deployment that's referring to my secrets, pick a node, and start to construct that pod. Now, what's inside that pod? Well, first we need to mount the secret. We refer to our certificate. So you know what? I want to be able to reference those certificates at this point in time. Now, this will be mounted in memory, so that way when the application goes away, there's nothing left on the disk. This is important. And then we take the secret and we extract it to the path that you specified in the deployment, right? So now this is how we get things in the right place. All right, our application expects those certs to be in a specific location. Then we get an IP address for the entire pod, including our app, and then we start our secure server, right? Right, these are the things you would normally have to do by hand. So how do you deploy the secure server? Here, we'll start with our specification. We'll grab one. We need to expose it to the outside world. So in Kubernetes, we have this thing called a secret. And the secret allows us, or a service, allows us to expose our applications and also handle service discovery. Since the scheduler is randomly putting things in place, we need a way to find them and make sure users can hit them. And then our gRPC clients can come in at the top. So let's do this really quick. I'm going to show you how to do this with Kubernetes. So what we need to do now is go to Kubernetes. Now, ahead of time, I created some Docker containers for these things. So in my Docker containers, you'll see these things. Oh, I have lots of Docker containers, don't I? But you notice my containers are like 11 megs. That's like impressive. And how do you get containers to be that small? First of all, you don't put a whole operating system in there. That's step one. The next thing you need to do is do your builds outside of Docker. If you do your builds outside of Docker, let me clear my screen really quick. The only thing you need to do is copy in your artifacts. In my case, I'm using Golang, so everything is statically linked. I don't need to bring in Debian and Ubuntu to do this, right? I can just bring in my binary, and the binary will execute. It's just Linux. You don't need all those things, especially if you don't have dynamic libraries to search in your path. Or some people include their dynamic libraries and still create this self-contained image. All right, so now we need to create our secrets. So in this directory, I have those secrets, my certificates and my JWT public key. So what I'm going to do now is kubectl create secret. I'm going to make it a generic secret, and I'm going to name it secure server, okay? And now I'm going to say from file, secrets. All right, so it's going to take everything in that folder and create a key value. The key name will be the file name, and throw it into my secret store under the key name secure server. I hit enter here, and now I get a set of secrets created, right? So these objects now live inside of Kubernetes. I can look at those, kubectl, describe secrets, and this is called secure server. Right, so I see my secrets, and I have 3 things in there, right? I have my key, my certificate, and my PIM. The other thing I'm going to do ahead of time so I can save time is create a service. I know people in the outside world are going to want to hit my application. So what I'm going to do is I have a static IP that I have already reserved, and I'm going to ask it to create a load balancer in my cloud provider of choice. If you're running on bare metal, you'll probably use some implementation with like F5 or some upstream thing you have. We also have integrations with HA Proxy or Nginx. But the idea here is that you will specify a way to expose your applications. Now, how do we find our app? This is where this label is important. We don't know where the scheduler is going to place our app, so we need a way of discovering where they are. And this is what this label does. When I create this object, it's going to watch our API server for pods to come up to have that matching label set. All right, so I'm going to create this now. kubectl create -f services secure server. So at this point, I have what we call a service. And this service is going to create a load balancer behind the scenes. And if I were to describe this service, we'll see that number one is creating a load balancer. And we don't have any endpoints because we don't have our application deployed. So it found nothing in the system. And it's almost like a real-time watch. We watch our API server. If anything appears, we update the backend. All right, so now let's deploy our application itself. So here's a deployment. So in our deployment is where we describe the application set. So we have a deployment. It's called secure server. We only want one copy of our app running. Here are labels that we're going to give the apps when we start them. App equals secure server. And then here's a list of containers. One is the secure server container. I built this earlier, pushed it to Docker Hub. And the flags, I just put them here so you can see that I'm actually looking in my pod for these particular files. And then here's where I specify the volume amount that I want. So where are those secrets going to come from? Right? All those certs are going to come from a secret, but I need to have it bind mounted in for me by my underlying runtime, which is the kubelet in this case. So down here, I can refer to my secrets that were pushed earlier into Kubernetes. So when I deploy this particular deployment, the underlying kubelet that runs on every machine will talk to the API server, grab those secrets, put them in a temporary file system, and inject them at this particular path. And each of the keys in that secret will become files underneath that directory. Therefore, this should just work, okay? The other things I'm going to do also are liveliness and readiness probes. We want to make sure our app is actually healthy. So those are now in place. So let's start this off. So kubectl create -f deployments. All right, so at this point, we have the deployment. Now, deployments are where we manage everything about that actual application being deployed. How many copies we want, what version, just to keep it simple. So kubectl get pods, all right? So it says it's up and running. That means it passes readiness check, and it's a health probe. Now, we can also do -wide if I care what node it's on. So I can see that it's running on this particular server. But that's of zero interest to me because I have a way of finding the application through the service. So now this is up and running and it's healthy. If I were to describe my service again, you notice we have an endpoint here, right? If I were to scale the application, actually, I'm going to do it the right way. I'm going to do this on the deployment itself. So I'm going to go from 1 to 3. The reason why I'm doing it here is because you can check these things in the GitHub and automatically process them. So now I'll do kubectl apply -f deployments secure server. So now we changed our requirement from 1 to 3. If we do get pods here, we'll see that 2 additional got deployed. Where are they running? I actually don't care, but if I wanted to know, -wide. So now we have 3 of them running in our cluster somewhere, all right? 2 on the same node, 1 on a different node. Now that they're running, we can see that they automatically get picked up by our load balancer, right? We don't have to register our apps. We don't have to go in a circle and figure out where things are. It's plumbed through the system automatically, all right? Now, let's say you want to get the logs for your application, right? So what I can do is call kubectl logs and view the logs for a particular set of containers. So here, we see that the application started successfully, and we see that Kubernetes is monitoring our application for us. So when I built my app, I made 2 endpoints, -help-z and -readiness. What do? The point of readiness is to say that my app is actually ready. Now, readiness can come and go. Let's say some dependent service you depend on is down. You're not ready to take traffic anymore, but it doesn't mean your app is dead. It just means it's no longer ready. So in order to play with that really quick, I'm going to change the readiness state of this and we'll see what happens. So let's do this. So what I'm going to do now is I'm going to port forward to one of my admin ports on this particular container so I can change its readiness state. I'm doing this so I can actually just have access. So I'm going to do this one. So what I'm going to do now, there's a command called port forward that I can get to a private port running inside of my cluster. So when I do this, I'm going to call curl. I'm going to change the readiness for this thing to 500. I want it to fail. So instead of returning 200s, I'm going to return 500s. Now when that happens, let's say your cache is down or something like that. And what we'll see is we'll go into a different state. Let me just do a watch. All right, so you notice that none of them are ready here. So what happens? What do we expect the rest of the system to do? Well, we want it to be smart. We describe the service, and you notice it's automatically removed, okay? Now, what happens if we were to, let's say, cause it to no longer be healthy? So I'm going to change help-z to return 500. So now we've caused the pod to no longer even be healthy. And watch what happens. kubectl, describe, pods. So notice that we're failing our health checks now. So it's telling me that it failed its health check with the 500. It's going to try that 3 times. And if it doesn't work, what do you do when that happens to you? You probably grab some logs. What else? What's the thing that fixes all broken servers? You restart it. So why not just have Kubernetes restart it? So right now it's going to fail a couple more times. And what you'll see is Kubernetes go and kill that pod and run it somewhere else. Maybe there's something wrong with that host. Maybe it's a temporary failure. We're just going to restart it. Now you can adjust that policy on when you restart. So now that that's been restarted, we try again, we go through our health probes, and if it's healthy, we leave it alone. And what will happen is if you have a node that's bad, where it can't get out to the network for some reason, and all the pods have to go through this cycle, they will all just get moved somewhere else where they can actually run healthy. And what you're going to get this whole time is a bunch of events streaming out saying, hey, this thing is dead, it's been moved, and now it's running fine. You're not waking up anymore, all right? So the last thing we're going to do is actually hit the service using our client, and then we're going to show how we update these things that are running real time inside of our cluster, okay? So now that we have the app running, kubectl, get service, we have this public IP. Now, this should work with my standard app. So we'll come here and bin, and we have the secure client. And then we're going to give it our server, okay? And then that's on port 10,000. And then we'll also give it a name that we want to say hello to, just my first name this time. So it connects and says hello. That works fine, all right? Just like it did locally. Everything is plumbed through, my token is going up, everything's being verified, but now we want to upgrade it. So how do you do that? So since we don't know where these things are running, we don't want to go manually touch servers or containers, we can update the deployment. So here, we'll stay at 3. Now, I'm just going to do an in-place update. There's other patterns for doing this, but to keep life simple, I'm just going to do an in-place update. I'm going to update to the version 2 of that particular gRPC service, but this time I'm going to actually use some data out of the token, ideally my email address. So I'm going to save this really quick. And remember what was in my token. There was a claim there. So inside of my claim, my email address was that, right? So I should be able to extract that out and reply to the user with it. All right, so now what we'll do is say kubectl, clear, kubectl apply -f deployments, and we're just going to update it. Now what will happen is our deployment will see that we need to do a rolling update of our application. Kill one, roll them out. while that's happening, it's going to happen really fast. I'll show you a visual of what that looks like. Visually, it looks something like this. So this is our current state. We did that update. It's going to add a new pod, so now we have 4, which is okay, but it's going to work hard to get back to the desired state. It's going to kill one of the other pods. After it goes through its health check, we'll get attached to the service. So remember, we only get to the service when we're healthy. Then we'll detach the other one because the probe is marked no longer ready because I'm about to kill it. It goes away. And we repeat this process until we roll the entire cluster. The scheduler knows how to find, or the controllers know how to find and delete the old ones and upgrade to the new ones. All right? So if this rolling update is working, we'll run this again. And we see now that we're getting our token here. All right? So now the last thing we want to do is, what happens if that was a bad release? You're like, that didn't quite work well. We shouldn't have fired all the QA people. Don't fire QA. Let's see. And then we'll sleep for 1 second. Done, okay? So people actually don't like to see their email address all the time, all right? And plus it's the wrong email address. So what we'll do here is we'll undo that. So kubectl rollout, we'll look at the history for my deployments, secure server, and we see that we have 2 revisions. And what I'm gonna do is just go back to the old one. So what I'm going to do is say rollout, undo. I can give it a specific version, but I'm just going to go back to the last one. So this says, hey, go back to what the last one was. If we had 100 of these deployments, we can actually specify the revision number, and it will go back to that particular revision number. And what you end up with is kube get pods. And we'll see that these start to die. It's too fast. They die and come back, but you'll see that we got a disconnect because we killed one mid-flight. But we see that we've rolled the entire cluster, so as we're hitting the pods, our service is no longer getting the new version. We're back to the old version. All right, and with that, I will end the presentation. Thank you. There's like 3 minutes for Q&A, and there's a mic here.
Does Kubernetes supports auto shrink and auto expand?
All right, so the question was, does Kubernetes support auto scaling, right? So there's 2 forms of auto scaling inside of the Kubernetes framework. There's one for the pods, what triggers a pod going up and down, right? So ideally, you see the API, and we did everything through YAML files in the command line client. But ideally, you could hit a REST endpoint by that deployment name and change that number up and down. So ideally, if you wanted to do it yourself, you would track some external metrics, set some triggers, and up that down. But in Kubernetes, we have a thing what we call HPA, which is horizontal pod autoscaling, where you can set things like CPU metrics. So the only thing we support today is if the CPU load goes above a certain point, then we trigger a horizontal scaling.
So based on the traffic, okay, so in the runtime, real time, so during a daytime, you will get a traffic like millions of requests, whereas in the nighttime, the traffic might be go down. So how the auto expand and auto string that Kubernetes supports?
I think we're out of time, so I'm going to answer it out there. Thank you.